Hi, good day to our lecturer. We are from Group 9 and today we're going to present regarding FSM and shift register. This is our group members Vinkeshwar Anlaki Saravanan, Nelson Anlaki Nyanandas, Mukesh Anlaki Prakash, and myself, Roshan Kumar Anlaki Navin Kumar. Okay, let's get into the topic of hand. In the grand tapestry of modern technological marvels, digital electronics stands as the crowning jewel, an omnipresent force that orchestrates the symphony of our daily existence and prospers the relentless march of progress across myriad industry. This awe-inspiring field, at its very essence, revolves around masterful manipulation and preservation of binary data through the artful arrangement of electronic circuits. The bedrock of this digital domination is forged from the foundational elements of logic gates, multiplexers, and the indomitable flip-flops, veritable guardians of information capable of safeguarding a solitary bit with unwavering vigilance. Flip-flops in their infinite wisdom serve as the linchpin in the creation of sequential circuits, technological marvels whose outputs are not merely beholden to the present inputs but are shaped by the echoes of input past. This transcendent quality imbues flip-flops with an almost mystical significance, rendering them indispensable with an expansive array of applications from the humblest data repositories to their most intricate state machines and counters. Now we are going to look into flip-flops. There are many types of flip-flops. Firstly, it is called SR flip-flop, which is also known as set reset flip-flop. Set reset flip-flop employs dual inputs to command the stored value. It is simple and foundational, used for basic memory storage. Secondly, we have G flip-flop, which is also known as data flip-flop. Data flip-flop captures the essence of its data input with clockwork precision. It also ensures predictability by always producing an output identical to the data at the moment of the clock pulse. Thirdly, we have G flip-flop, which is also known as toggle flip-flop. Toggle flip-flop switches between states with a clock pulse. It is also useful in binary counters and logging operations. Thirdly, we have JK flip-flop, which is also known as Jack Kirby flip-flop. Jack-Kirby flip-flop is versatile and can assume the roles of other flip-flops. It is also known that known for its ability to avoid the undefined states of the SR flip-flop. It, it is also integral in design of counters and complex state machines. Flip-flops are crucial in digital electronics, playing a pivotal role in the storage and transfer of data with circuits. Each type offers unique advantages, making them suitable for various applications from simple data storage to complex fluid state machines (FSMs) and shift registers. In the industrial realm of flip-flops, the JK, known as Jack Kirby flip-flop, stands as the epitome of versatility and functionality. Renowned for its capability to emulate the behavior of other flip-flop types, SR, T flip-flops, and the JK flip-flops is a paramount component in the design of complex digital circuits. The JK flip-flop's primary advantage is its ability to toggle its state based on the inputs J and K, making it an essential tool in applications that require precise control of its state transitions. The particularly useful in the creations of sequential circuits where a state progression is a fundamental requirement. Its key characteristic is its versatility. It can function as a SR, T, or T flip-flop. Secondly, its toggle capability. Its state changes on the clock edge if both J and K are high. Thirdly is the reliable operation. It emulates the ambiguity present in SR flip-flops when both inputs are high. Its applications: finite state machines, known as FNMs, utilized in the designs of counters, shift registers, and other sequential circuits. Secondly, counters. It is ideal It is ideal for designing binary counters due to its reliable toggling mechanism. Thirdly, state machines. It is effective in implementing state machines like traffic light controllers and other control systems. The JK flip-flop is a cornerstone in digital electronics, providing a robust, adaptable solution for various applications, from simple data storage to complex state machines, underscoring the indispensability in modern digital circuit design.
Now I'm going to talk about FSM machines are crucial in digital electronics, providing structure models for predictable state transition and control. They are defined by the infinite set of states, transition, and this state driven by inputs and outputs that can be depend on the current state. And the key concepts are states represent different conditions and statuses of the system. Transitions define a moment between states based on their input signals, and outputs are determined by the current state influencing system behavior. In the type of FSM, there are only two type of FSMs, which is more as machines and mainly machines. More machines means output depend only on the current state, and the mainly machine means output depend on the both the current state and input. The application of traffic controller. Traffic controller exemplify FSM amplification. They manage traffic light, timing, and sequence at intersection, ensuring safe and efficient vehicle and pedestrian movement through the control transition between states, representing different phases of the traffic cycle. Traffic light controllers utilize FSM to manage traffic light flow efficiently and safely through structured state transition. State and transition. Green state allows vehicle in one direction to proceed. Yellow state signal a transition to red, warning drivers to prepare to stop. And red state require vehicle to stop, allowing cross traffic to proceed. State transition logic. Green to yellow transition after set duration. Yellow to red follow the yellow state. And red to green initiate the cycle of the either initial or cross traffic direction. Advanced features of the traffic light. Timing, dynamic timing. The sensors adjust light timings based on the real-time traffic condition and optimize flow. And safety efficiency. FSMs ensure predictable sequences, preventing accident and manage traffic effectively. By designing FSMs tailored to traffic patterns and safety needs, engineers create robust control system for traffic light, enhancing urban mobility. In finite state machines are integral in traffic controllers, managing light timing and sequencing at intersection. Functionality. Green state allow movement in one direction and yellow state once of a pending red light. As you know, red light requires vehicle to stop. And register. Shift register sequences of flip-flop. For example, CISO, ISO, I mean like SISO, PISO, SIPO, and PIPO. Example of 4-bit parallel in load recirculating shift register using 7476 JK flip-flops. Practical application. Stimulation tools. Logism and Tinkercad stimulate FSM and shift registers. Educational value enhancing understanding of digital circuit design. And components are JK flip-flop, verticile or for robust digital circuit. And FSMs are more machine and main machine. As you know, the more machine output depend on the current state and the mainly machine output depend on the state and the input. That's all for me. Thank you. So
Definition of counters is sequential circuit that traverse a predetermined sequence of state, each state representing a unique combination of binary values. There are two main types of counters, which is a synchronous counters and asynchronous counters. For asynchronous counters, the flip-flops within the counter are not clocked simultaneously, and for the synchronous counter, All flip-flops are clocked simultaneously. A 3-bit counter using JK flip-flops includes the following components, which is JK flip-flops and clock pulse. A state representation for the following counter is 3-bit binary number representing counts from 0 to 7. This is flip-flop transition table. State diagram. A state diagram is a visual representation of finite state machine. Here, it illustrates a 3-bit counter using JK flip-flops, cycling through each state from 000 to 111, based on clock pulses. JK flip-flops toggle their state with each clock pulse if both J and K inputs are high. Each state represents a 3-bit binary numbers, transitioning sequentially from 000 to 111, and then resetting to 000. The diagram shows circles for each state and arrows indicating transitions triggered by clock pulses. This visualization helps in understanding and designing the counter's behavior in digital system. So these are the K-maps, which is Karnaugh maps, are powerful tools in digital electronics used to simplify Boolean explanation and streamline logical functions. They work by grouping adjacent cells with identical values, revealing simplified expressions crucial for efficient circuit design. In this project, we apply K-maps to JK flip-flops, which are fundamental in finite state machine and shift registers. These flip-flops change state with clock pulses, forming the backbone of complex digital system. Our approach began with constructing a state table and excitation table for the JK flip-flops, detailing the required J and K inputs for each state transition. Using K-maps, we visualize and simplify these inputs, creating efficient Boolean explanation for each flip-flop.
Good day. I'm Nikeshwar Analaki Saravanan, matrix number AA232524. I'm here to present about the FSM circuit. So let's get ready to be amazed by our finite state machine FSM design, which use LEDs to visually represent state transitions in a way that both beautiful and logical. Each LED corresponds to a bit in a binary number, which the leftmost LED at the most significant bit MSB and the rightmost at the least significant bit LSB. This setup makes it easy to see and verify the FSM's state sequence. We designed the state transitions using Karnaugh map K-maps to simplify the Boolean expressions for each flip-flop input, leading to an optimized and error-free design. For example, we simplified the JC input to JC is equal to QB plus QA prime, meaning the J input of flip-flop C is high when QB is high or QA is low. Similarly, the KC input is simplified to KC is equal to QB prime, meaning it is high when QB is low. These simplifications made our FSM design more efficient and reliable. As the FSM operates, the LED light up in a specific sequence 000, 101, 001, 011, 100, and then it repeats. Each state is shown by a unique combination of LEDs, which the MSB LED shining brightly, while the other LEDs flicker in sync. For instance, in state 000, all LEDs are off, representing binary 000. In state 101, the MSB and LSB LEDs are on, while the middle LED is off, representing binary 101. This setup allows us to easily track the FSM states transition. Next, the LED sequence confirms the correctness of our FSM design, showing that the excitation map and K-max simplifications are working perfectly. For example, when moving from state 000 to 101, the excitation inputs guide the flip-flops to the correct next state. The visual confirmation proves our FSM behaves are intended. The cause of the display in the JK flip-flop whose inputs were derived from K-maps analysis. Simplified Boolean expressions for inputs like JC, KC, JB, KB, JA, and KA minimize the required logic and reduce potential errors. For example, we simplified JB to JB is equal to QC prime QA, meaning the J input of flip-flop B is high when QC is low and QA is high. The KB input is simplified to KB is equal to QC plus QA, meaning it is high when either QC or QA is high. These simplifications ensure correct flip-flop operation. As the LED lights up in perfect harmony, they demonstrate our engineering skills, validating the FSM design and highlighting the elegance achieved through K-maps and digital circuit optimization. The LED display showcases the complex logic behind our FSM, allowing viewers to appreciate the beauty of digital system. This project fills us with pride and accomplishment, pushing the boundaries of digital electronics. Now we are going to see the elegance and efficiency of the parallel in, parallel out PIPO shift register, a brilliant example of sequential logic design that showcases the power of digital electronics. This clever circuit handles data storage and movement with exceptional speed and simplicity, transforming the way we manage information in digital technology. At the core of this impressive creation are the 7476 JK flip-flops, each capable of storing a single bit of data and syncing with a common clock signal. These flip-flops, carefully arranged in our PIPO shift register, allow for the simultaneous loading and output of multiple data bits, maintaining data integrity throughout the process. The 7476 JK flip-flops, which its various inputs J, K, clock, clear, and presence, provides precise control and configurations for our PIPO shift register design. The operation of the system is a precise and timely process. First, the parallel data inputs are fed into the flip-flops, each bit taking its designated place. Then, with a clock pulse, all flip-flop stores the data simultaneously, like a perfectly synchronized dance. This result is a rapid transfer of information to the parallel outputs, ready for use in demanding digital applications such as data acquisition systems and communication networks. The schematic of our people shift register is a well-designed network of components that works seamlessly together. Each 7476 JK flip-flop is set up to correctly interpret and store the parallel data with the J input connected to the data input and the K input to its complement. This setup ensures accurate data storage during the clock pulse, reducing errors and enhancing system reliability. The common clock signals coordinates the flip-flops, ensuring synchronized operation and data integrity. The clear and press inputs, usually inactive during normal use, help initialize the flip-flops to a known state ready for data processing. The parallel outputs representing the stored data bits are ready for further use in the digital system. This PIPO shift register designs offers several benefits. It enables fast data loading and output, ideal for time-sensitive applications like high-speed data communication and real-time control. This parallel input and output design simplifies the system, making it easier to integrate into larger digital architectures. Whether for data storage or efficient data transfer, the People Shift Register is a versatile and essential tool. Its ability to handle multiple data bits simultaneously with precision and reliability makes it a standout in sequential logic design. We take pride in our creation, knowing it advances digital electronics and paves the way for future innovations. The People Shift Register is a testament to engineering skills and digital design beauty, set to inspire for future generations of engineers. As a conclusion, the parallel in, parallel out People Shift Register represents the peak of our digital engineering efforts. This impressive creation highlights the perfect blend of theory and practice in modern electronics. Successfully designing and implementing this People Shift register with 7476 JK flip-flops showcases our team's creativity and hard work. By exploring this key component, we have mastered synchronous data handling, where each flip-flops work together harmoniously like a well-coordinated orchestra. Our 4-bit People Shift register, an example of efficient parallel processing, is designed to load and output data simultaneously, improving the speed and efficiency of digital data management. This parallel processing power sets a new standard for data transfer and storage in various applications. Validating our design with LED sequence has provided a clear visual confirmation of the underlying logic, proving the correctness of our Karnaugh map simplifications and excitation map derivations. This successful hardware and software integration is a true mark of engineering excellence. We take great pride in our creation, having turned theoretical principles into a practical, high-performance solution. The knowledge gained from this project will drive further exploration, where integrating people shift registers with other digital components will enhance data handling and processing capabilities. The people shift register demonstrate the power of synchronous logic and the beauty of sequential circuit design. This achievement will inspire further engineers to dream bigger, innovate more boldly, and develop solutions that will shape the digital world. That's all from me. Thank you.